Hi everyone, we are Team 1 and this is our progress presentation. We have studied the methods to improve a BCI-based quadcopter using head orientation. The presentation will proceed in the following order. BCI is a computer-based system that acquires, analyzes, and translates brain signals into output commands in real time. With BCI-based robots, even people with severe motor disabilities can interact with the environment. The purpose of the paper, quadcopter control in three-dimensional space using a non-invasive motor imagery-based brain-computer interface, is to control a robotic quadcopter in a 3D physical space by means of a motor imaginary EEG-BCI. It is the first paper demonstrating the ability to control a flying robot in 3D physical space using non-invasive scalp-recorded EEG in humans. It has become a basis of a follow-up research drone studies. The control scenario is to navigate the quadcopter to pass through a ring. The trial fails when the drone collides in the ring or deviates from the boundary of the control space. Imagining clenching of the hand is used as the control method. Because there are no standard evaluation criteria for follow-up BCI area vehicle studies, we choose the Massachusetts basis paper as a target paper for our project. Also, the studies share the same limitations. First, although motor imaginary is an intuitive BCI paradigm, the control systems with using it is unstable. Heavy user workload and individual difference in accuracy is other problems if control only BCI. Our approach to improving the performance of a BCI-based quadcopter is adding extra information that might include the user's intention. The paper we choose proposed a method that uses only motor imagery to control or drone's movement. Our proposed method adds our head orientation information of the user on top of each information when decoding user intention to help improve the drone control's performance.
Next content is our replication progress. According to our plan, we replicate the work in simulation environment. We implement the simulation environment using Unity for controlling a motor imagery-based quadcopter. We use quadcopter asset to replicate a drone object and create a track with evenly distributed control command. Next is our method. We use brain vision software to take brain signals information from the user in a reliable manner. The commands are 4 classes, which are rest, right hand, left hand, feet. The overall data process is as follows. When the user imagines a body movement, we receive EEG data for the last 2 seconds per 1 second. Then filter the EEG data to pass only frequencies between 4 to 38 Hz. About the pre-processed data, we perform classification using ShallowNet. The result from this output will convert to the actual control commands such as forward, stop, right, left. The command will update only when the same command comes out twice in a row. The figure shows the user controlling the quadcopter with brain signals in the pilot test.
Next up is improvement progress. In order to know about how users' head move when they control a virtual drone, we created a course for the users to complete using a keyboard. While the users control a virtual drone to complete the course, head orientation of the users were recorded with the drone command they were pressing at the time. This gives us a huge number of pairs that consist of head orientation and drone command. We thought this will give us information about where the user's head directs to by their intended movement direction. This is the pilot test result. We had to first make sure that the head orientation of the user can give us information about where they're intending to head to. So after asking 3 random participants to complete the course with a keyboard, we were able to analyze their head direction by their movement. Plots on the slide is a probability density function of users' head orientation by head angle. X-axis represents the head angle of the user and Y-axis represents the probability density. Orange line denotes user's head angle distribution when they're turning the drone left. Blue for the forward movement and green line for the right turn. This shows that user's head orientation differs by intended movement because you can see that 3 distributions of each plot have clearly different distribution, which means that head orientation of the user differs by their intended direction. So here's an overall scheme of our improved approach. We basically merged 2 methods of predicting the user's intention. First, we have EEG, which is classified by a classification model called Shallow ConvNet to come up with a scaled softmax output by EEG to represent the probability of user's intended action, which is based on EEG. The output is scaled using temperature scaling to better represent the probability. For another source of inferring user's intention, we have head orientation theta. We have probability density functions to predict the probability of user's intention based on his or her head orientation. And for a given head orientation theta, we take probability density value of the theta from 3 probability density functions. The red line here shows you how a theta value can determine 3 probability density values from the probability density functions. So this gives a predicted probability of each drone command being user's intention based on head orientation. We're going to prioritize the EEG classification result as it is a direct source from the user's brain. If rest is the maximum value of 4 outputs of the classification model, the drone will remain still. If not, take the dot product of right, left, forward output arrays from each source and take the maximum value of the dot product. The result of drone command is either going to be right, left, or forward. This way, we can use EEG to predict whether the user is intending to remain still or move. And we can also use head orientation on top of EEG to better predict where they're intending to move to. So here's our brief plan for the experiment. We're going to be comparing 2 methods of BCI control in the same course. So one of the methods obviously being the traditional one and the other one being our improved approach. So one of the 2 metrics is time spent to complete the course. And if they can't complete the course, we're going to compare how far they can go. And this is considering the fact that not many people are familiar with using brain signals to control an object, which usually leads to low performance. We are actually assuming at this point that not many people will be able to finish the course when using brain signals only. So we thought this extra metric could help us better analyze the result, even the participants aren't able to finish the course. We're going to be testing on people that have no prior information about how this method works. If the participants are aware of the fact that their head orientation affects the drone command, it won't be a fair comparison. So this is our brief plan for the experiment. And from now on, we're going to be finding people to experiment our method and compare and analyze the result. And this brings us to the end of the presentation. And thank you so much for listening. And this is tentative plan by the week. We're at the experiment stage. So we are kind of catching up on our schedule. And here's our reference. And thank you so much for listening.